the symbols that we will be using in asymptotic notations. So asymptotic notations has to deal with mathematics. Like this is not a actually topic of algorithms or some data structures or algorithm particularly. It is a topic of mathematics. Why? Because these symbols are mathematical notations. These are not related to data structure or algorithms. But then why we are using them in data structures or algorithms? Because we will be representing our time complexity or space complexity as a function. Okay, as a function. So function of what? Function of input size. Okay, now first tell me what is this input size. Let me ask you some question. Suppose that you have some linked list. Okay, and your algorithm is to insert in the linked list. Now for this algorithm what you will be giving? Maybe you are inserting at the middle. At middle. For this algorithm what you will be giving? You will be giving linked list. Maybe you will also giving the value. So what is the input of this linked list? What is the input size of this linked list? Like input is linked list and value. What is the input size? Input size is basically linked list length, which is n, and this value, which is 1, right? So input size is n plus 1. So overall the input size is actually n. Like these are the constants, so you can ignore it, right? So you can say your time complexity, which is generally represented by t, is a function of n. Why? Because n is an input size. Now if I ask you another question, suppose you need to multiply two numbers. In this case, what is input size? Input will be how big your numbers are, right? Suppose one number is this much big, another number is this much big, then you will say, suppose that first number is having length, the number of digits, maybe you can say number of digits. First number is having n digits, second number is having, let's suppose, m digits. Then your input size is actually m plus n, right? This is your input size. Now your time complexity will be in the like whatever is bigger. Generally like we will take the max, just in the case like n plus 1, n is the maximum. So similarly we will take the max, otherwise you can have the time complexity in terms of m comma n, because both are the inputs. So your time complexity or space complexity will be of the function of input size, right? Suppose you are given with a graph and you need to check, like there could be any algorithm, but suppose there is an algorithm which checks whether the graph is bipartite or not. Okay, so you are giving a graph as an input, which means you are giving number of vertices, like total vertices and edges, right? So this is your input. Now your time complexity, suppose the number of vertices are n, number of edges are m, your time complexity or space complexity will be in the function of mn, right? Now similarly there could be actually any algorithm and there will be different inputs. So your input size is basically the size of the input, right? Now your this time complexity and space complexity will be represented in the input size, which means this time complexity is a function of input size. And since I'm representing this as a mathematical function, that's why we need to take help from the mathematics. So these are the symbols from the mathematics. So I will be taking help from the mathematics. So I will say that T of n is basically maybe order of, so big O of some number, maybe let's suppose n square, some function. So these two are functions. This is a function, this is also a function, and this is a mathematical notation, right? So that's how we will be relating this mathematics and algorithm or data structures. Okay, I hope you got it. So let me just go over these symbols one by one and I will explain these in detail. Let's have first notation, which is big O notation. So what is a big O notation? It basically says Tn is order of Gn if there exists a constant c greater than 0 or n not greater than equal to 0, such that for all n greater than equal to n naught, Tn is less than equal to c into Gn. Now I know that you haven't got it anything, so let me explain it clearly. So Tn, I say, is order of some function, maybe n square. If and only if I am 100% sure that Tn, like whenever I'm writing like this, then I will say that Tn, which is my time complexity, right, which is basically time complexity. So I will say that Tn, or time for my algorithm, can be at most n square for any input. So what do I mean by that any input? I will just explain. So for now, just understand this, that whenever I'm saying Tn equal to order of n square, then it means that Tn is less than equal to Cn square, which means my time complexity will always be less than equal to n square, right? At most I can take n square time. So what do I mean by at most? See, let's suppose, again take an example of linked list only. Let's suppose you are inserting in a linked list, right? Suppose this is the linked list that is given to you, and your algorithm insert in the linked list and at the given node. So suppose that this is having some value which is 1, maybe this is 2, this is 9, this is 11, this is, let's suppose 13 or anything. Okay, now suppose you want to insert before 13, insert before 13, then how much time you will be taking? You will be iterating over all the nodes and you will be taking order of n time, total n time. Let's not worry about the order and all. So you will be taking n time. So if your input is insert before 13, then you will be taking almost n time, because you need to iterate till 13, because you will run a while loop till this point and then you will be inserting. Suppose you want to insert before 2, then you will just go here and you will just insert before 2, right? So it will just take a constant time, maybe, or maybe just one time, right? So depending on the input, if input is insert before 13, then you will be taking n time. If input is insert before 2, then you will be taking 1 time. So depending on the input, a simple algorithm or a same algorithm can take multiple times, different times, right? So algorithm is fixed, and depending on the input, maybe for the input 1, when you are saying that insert before 13, you are taking order of n. Okay, let's not worry about order. So you are taking n time, and the same algorithm for the different input, different input can take just a constant time or some other time, right? So it depends on the input also. So whenever I'm saying that Tn is order of n square, then it means that Tn is less than equal to Cn square, which means I never take more than n square on any input. So that is important, that I'm saying any input. So time complexity for my algorithm can be at most n square for any input, which means whatever input I give, I am now completely worry free. I do not have any tension, like whatever input I give, I have bounded my time complexity that it will not take more than this time. Isn't it useful? Like in the practical scenario, just think about it. If I just ask you, if your manager asks you that how much time your algorithm is going to take, then instead of listing down all the inputs that okay, for this input it will take this, for this input it will take this, for this input it will take this, you can just say my time complexity is order of n square, and your manager will understand this because he's your manager, right? So he will get to know, okay, your algorithm will never take more than n square, right? So that's where this symbol or this notation is very useful. Now in mathematical sense, I say that Tn is order of Gn whenever I can write Tn is less than equal to C into Gn. So what is a C? C is any constant which is a positive constant basically, okay, greater than 0. And n naught is some bound, or I can say turning point. After that, this is always true. So let me just explain you what I'm trying to say. Just see at this graph. See, if you compare C into Gn and Fn, then what you will say that which is greater? If we are standing here, then you will say that okay, maybe this Fn is lesser, Cn is greater, right? C into Gn is greater. Maybe you are standing at this point, you will say okay, Fn is greater and C into Gn is lesser. Maybe at this point you will say both are equal. And maybe after this n naught, okay, after this n naught, suppose you are standing here, here, or here, anywhere, you will always say that C into Gn is greater. For example, let me take an simple example of maybe a function which is n square, which is, let's suppose, fn, and maybe another function which is, let's suppose, 2 power n, okay, and this is C into Gn. Maybe C could be, you can say C could be just 1 here in this case, but that is okay, this is C into Gn. Now let's just see what is happening at n equal to 1, at n equal to 2, 3, 4, 5, 6, 7, like that, right? So what is happening at n equal to 1? what is the value of n square and 2 power n? So you will say that n square is 1, 2 power n is 2. Here it is 2 power 2 square, it is actually 4, it is also 4, right? Here it is 3 square, which is 9, it is 2 power 3, which is 8. Here it is 4 square, which is 16, it is 2 power 4, which is also 16. It is 5 square, which is 25, it is 32. It is 6 square, which is 36, but it is 64. It is basically 7 square, which is 49, and it is 128, and so on, right? Now you observe one thing, that if you are comparing at n equal to 1, then you will say that okay, 2 power n is greater, but here both are equal, here it is greater, here again both are equal, here it is greater, it is greater, it is greater, right? So ultimately, which one is greater? 2 power n is greater. Why? Because after a certain point, 2 power n is always greater. You can compare for any value. Okay, 2 power n is always greater. Before that certain point, anything is happening. See, sometimes 2 power n is greater, sometimes both are equal, sometimes this is greater, sometimes both are equal, right? Before this is called turning point. Okay, this is called turning point. Let me mark it here. This is called turning point. So before this turning point, anything can happen, but after this turning point, this function is only greater, right? C power n is only greater. So you can say yes, fn is less than equal to c into gn. Why? Because c into gn is always greater after some turning point. Before some turning point, I actually do not care. Why? Because these asymptotic analysis and all, these are for our large input. So basically, we do asymptotic analysis for large input, which means we actually do not care about the small input. Just think about it. Why we do not care about the small inputs? Because for small inputs, anyway, it is going to take lesser time. Maybe 10 millisecond, one is taking 11 millisecond. Does not matter much, right? But when it is larger, when the inputs are larger, then it's going to take larger times, right? So 128 and all. So it will keep on taking larger time. So if input are larger, then time will also be larger. So that's why we care about the large input. At large input, how my algorithm is behaving. So that's why this analysis, this asymptotic analysis is basically suitable only for the large inputs, because for small inputs nobody cares. Okay, so no one is going to care how much your algorithm is taking for the small inputs in the practical sense. Now, if I am saying that fn is less than or equal to c into gn, then it means that there is some turning point after which it is true. Okay, I mean generally, like whenever we say fn is less than or equal to c into gn, which means there is some turning point after which it is true. So this is a turning point, right? If turning point does not exist, then I can say that okay, I cannot compare these two functions. I will tell you examples later, but for now just understand that if there is a turning point, then you can say yes, this function is less than or equal to this function. So c is some value, maybe in this case it is 1. I will tell you more examples where it will be some other value. Okay, so c could be some positive value and not could be also some number, but this should hold, which means you should be able to say that after some turning point, this is always lesser than, you can say it could be n square also, like because this function is always less than or equal to n square. So anyway, let me have some tighter bound, which means let me have a bound which is as close to as this function. So I will just prove it. It is actually order of n. So basically we need to find the value of c and n naught. If I can find the value of c and n naught, then this is actually true. Okay, before I start these examples, let me give you one disclaimer, which is that you will never ever need to find the value of c and n naught in your any of the like exam or something. Like, I mean, they will never ask you, and this is not be required in the practical sense also. But just for sake of understanding, we will have some example where I will be just finding the value of c and n naught. Okay, but I will tell you a method where you can just ignore, like basically you can just ignore these constants and you will never actually need to find the value of c and n naught. So anyway, let's continue. This is 3n plus 2, right? So 3n plus 2 should be less than or equal to c into n if I want to write something like this, which means, what do you think, what could be the value of c? See, you can say that okay, c could be maybe some big value, maybe 10,000, right? Maybe some big value. If you are saying that c is some big value, then I think it will work. I mean, this will be 3n plus 2 less than or equal to 10,000 n. I mean, anyway, it will be 10,000 n. Now, now the c is always a constant. Do not tell me that c equal to n. Let's take c equal to n or c equal to n square. Okay, do not say things like this to me. So because c is a constant, so you cannot take c as a function, and do not compare this c with n, which means you do not say that okay c is greater than n, or c actually cannot be greater than n, because c is some constant, however big it is, maybe 10,000, 10 million, 100 million, anything. Okay, however big it is, you can always have n greater than c, right? Because n is a variable, you just take n equal to c plus 1, right? C plus 1. So anyway, never compare this c with n. If you are comparing, then c is always lesser than n. C can never ever be greater than n, because c is just a constant. Okay, and n is a variable. You can always take n a value which is greater than c, right? Whatever c, however big it is, it does not matter to me. So anyway, coming back to this, if you are taking c as 10,000, then what will the value of n? I think maybe after 1 only, if you put n equal to 1, then it will be 5, it will be 10,000. Then after n equal to 1, so you can say n not equal to 1. So after n equal to 1, it is actually true. So you can say c is 10,000 and n is 1, right? For this pair, this holds, right? If you find any pair, okay, there exists c, there exists n, such that this holds, then you can say that yes, this is actually big of n. Okay, so instead of basically finding this much large c, maybe we can try some smaller c also. See, it is 3n, so maybe if I take c as 4, because this is 3n plus 2, if I just take 4, which means it will be 3n plus 2 less than equal to 4n. I think this should be true, because this is 3n and this is 4n. So ignoring the constant, it should be true, right? But for the after turning point, then definitely it will be true. So what will the turning point here? C is equal to 4. For that, can you have some n? Yeah, you can say n equal to 1000. I mean, you can also take this as a very big value. Then obviously it will be greater. But let's take some smaller values. For n equal to 1, I think this is 5, this is 4. For n equal to 2, this is 6 plus 2, 8. For this is also 8. Let's take n equal to 3. I think after n equal to 3, this must be true, right? So you can say yes, this is actually true, which means 3n plus 2 is actually lesser than equal to cn, which is as good as saying 3n plus 2 is equal to order of n, right? Equal to order of n. And if someone asks you what is the value of c, what is the value of n, you can say there are many values, maybe 4, 3, and earlier we have found 10,001, right? 10,001. And actually there are many values, 10,000, 10,000, 1,000, there are many values, right, for which it is true. So you can give any of that as an example. I hope that is fine. Now let's take another example, which is 1 plus n plus n square. Okay, and in this case also you want to find out that what is the value of c. Let's suppose I want to bound it to n square. So what is the value of c for which it holds? Okay, so you c and n naught, so you can say that okay, this is n square. If you take this as also n square, I mean this is actually this can never be basically greater than 3n square, right? So if you want to say that what is the value of c, then you can say c equal to 3. Why? Because this is n square, so you just treat these three terms as a 3n square, like just for sake of solving the problem. So it is 3n square and this is also 3n square, so basically it will be anyway lesser than 3n square, right? Because this is n square, this is not n square, but if you take this as n square, even if you take this as n square, then c will be 3, right? So now you just check what is the value of n. This is, if you check for n equal to 1, it will be 3, it will also be 3, 3n square is also 3, right? 1 plus n square. This is, if you take n equal to 2, then it will be I think it will be greater. So for n equal to 2 and c equal to 3, it will be true. So you can say this is actually true, and if someone asks you what is the value of c and n, you can say c is 3 and n equal to 2. Actually there are many examples again. C equal to maybe 4, n equal to maybe like you can check maybe 4, 5, maybe c equal to 1000, maybe n equal to also 1000. For this also this is true. So actually there could be many examples, we just need to give one example. And in fact, we do not even need to give one example, because nobody is going to ask you. This is just for our sake of practice. In reality, what we are going to do, we are just going to take significant term and we are just going to put the significant term here, right? Which is n square. You are just going to put the n square here. Okay, and this will always work. This will always work. And in fact, you can take a bigger than the significant term. You can also say this is also true. Why? Because this is less than or equal to c into n cube. If this is less than or equal to c into n square, then and definitely it should be less than or equal to c into n cube. Maybe c equal to 3, n equal to 2. This will also work in this case, right? You can just check it out. if you put c equal to 3, it will be 3n cube, and after n equal to 2, maybe you can say 2 1 plus 2 plus 4, it will be 7, and it will be like 8 into 3, it is 24 already, right? So after n equal to 2, maybe after n equal to 1 only it is 2, right? So anyway, like you can find out the value of c and value of n, right? So whatever you are putting here, you can always put greater than that, right? Which means if you are putting n square, you can put n cube, you can put n4, you can put anything which is greater than that. So I hope that is fine. Similarly, let's find out c and n for n plus log n. Now n plus log n, you can say, and let me just find out the cn and value for order of n. Okay, n plus log n is less than or equal to c into n. So just treat, see, this is not as good as n, but this is smaller than n, but just treat this as an n. So it will be 2n. So you can put the value of c as 2. It will definitely be working. So you can say that maybe after some n, maybe n equal to 10, or you can find out the value of n. Let's say n equal to 10. So c equal to 2 and n equal to 10, which means after this n equal to 10, it will definitely be true that n plus log n is less than or equal to 2 into n. Okay, maybe at n equal to 5 also it is true. You can just check it out. So anyway, like you can find out the value of c and n in this way, right? Now let's go to this slide. So here also they are asking find the value of c and n not for the below functions. So I think this we have done. Let's find out for this function. So this is 2 into n square less than or equal to c into n cube. I think the value of c, maybe you can just take 2, like I mean you can take 20,000 or anything, like does not matter, for just for the sake of example you can take 2, and maybe you can say that after 1 only it will work, right? Less than or equal to it will work, yes. So c equal to 2, n equal to 1, so this will work. What about this? 2 power n plus 1 equal to order of 2n. 2 power n plus 1 equal to order of 2n, which means this is less than or equal to c into 2n, and this is 2 power n plus 1 is nothing but 2 into 2 power n. So you can say that after c equal to 3 it should work, because this is actually cancelling it out, and c greater than or equal to 2, so which means you can say c equal to 2 or c equal to 3. So after c equal to 3 it should work, and n equal to 1, right? So n equal to 1, c equal to 3 is also answer for this case. What about the next case? 2 power 2n equal to order of 2n. Let's see. 2 power 2n equal to 2 power 2n equal to order of 2 power n, right? I think that was the example. Yes. Now let's just try to find out 2 power 2n is less than or equal to c into 2 power 2n, right? Now let's just try to find out the values of c and n. Now just see that if you just cancel it out, so it will remain 2 power n, and it will be basically c only, right? C. Now can you take a value of c which is greater than or equal to 2 power n? No, right? C is always lesser than some function of n, always lesser than some function of n. It could be any function. So that's why however large c you take, see, it does not matter, you can take this much large, I mean does not matter to me, because I can always take n value which is actually larger than this. Maybe you can put the same value here, so it will be very large, right? It will be very large. So c can never be greater than or equal to this 2 power 2n. So that's why you can say c does not exist in this case, which means you can not say that 2 into 2 power n equal to order of 2 into 2 power n. You can never ever say this, right? So that's why c does not exist in this case. I mean since c does not exist, that's why you cannot say. Okay, so I hope you got the answer, which means 2 power 2n is not a order of 2 1. Okay, which means it is not actually lesser than or equal to a 2 power 2n. Okay, so this is actually false, this is not even true. Now what about this? I think you can have some value, you can easily guess, maybe c equal to 101 and n equal to some 5 6, anything you can take, right? So anyway, this will work because it is 100n, and if you even treat this as an n, so you will say it is 101n, and then you can have a value of c and n, right? So similarly you can find out the values of c and n for these functions, right? Anyway, like these are just for example, we are never going to use this this technique to find out the value of c and n. In fact, we will never need to find out the value of c and n in our cases. Now let's move to a different notation, which is big omega notation. Just like a big O notation, big omega notation is also same, which means in big O notation I used to say that Tn is less than or equal to c into Gn, right? Or Fn is less than or equal to c into Gn, whatever. Here I will say that Gn, okay, this Gn is greater than or equal to 1 upon c into Fn. I mean both are actually same. If I'm saying that Fn is big O of Gn, then it is as good as saying that Gn is greater than or equal to, means Gn is big omega of Fn. So big omega means Gn is greater. So whatever is this constant 1 upon C or anything, like this should not be this should not be negative, or this should be greater than 0. So 1 upon C could be another constant which is C dash. So anyway, whenever I am saying that Tn is a big omega of Gn, okay, then you will say that Tn is actually greater than or equal to C into Gn. And these things are same, which means that if I am saying Tn is big O of Gn, then what does this mean? It means that Tn is lesser than or equal to C into Gn. Okay, I hope you got it. Now second thing is that if I say Tn, or let me say another function which is Fn, okay, if I say that this is big omega, this symbol is called big omega, okay, big omega of, let's suppose Tn, Gn or anything, Gn, then it means that Fn in this case is actually greater than or equal to C into Gn. That's the only difference. I mean, here it was lesser than or equal to, here it is greater than or equal to. Okay. So actually, if Tn is big omega of Gn, that is possible if and only if Gn is big O of Tn. Actually, this is vice versa, which means if we are putting this function as lesser than or equal to, if you are saying this is greater than or equal to, then you can also say that Gn is lesser than or equal to some other constant, maybe C dash into Fn, right? This constant happens to be 1 upon C, that is okay, right? So you can say that if this is greater than or equal to, then this is less than or equal to, which means if this is greater than or equal to means what? This is Fn equal to big omega of Gn. If this is less than or equal to means what? Gn equal to big O of Fn. This is called big O. Okay, big O. This is big O of Fn, right? So let's take some examples, and after that I think it will be clear. Before that, let me explain you with the graph. Now, this is Fn, which is actually greater than or equal to C into Gn. Why? Because after a certain point, Fn is always greater than or equal to C into Gn. Okay, let me take some example. Can you say that 2n square is greater than or equal to n square? Can you say? Yes. Yes, right? And what is the certain point? Okay, what is the value of C and n? See, this is Fn, okay, this is Fn. So what is the value of C? C is actually 1 here. Okay, if this is Gn, you can say for C equal to 1, because I am not multiplying with anything, and n may be equal to after 1 only it is true, right? For C equal to 1, n equal to 1, it is true, which means this is true. Okay, let me take another example. Maybe let me just erase this. Can you say that this this thing, which is, let's say that maybe 100 n square is greater than or equal to, can you say maybe 1000 n square, or let me just take it 10 n square, and can you say it is greater than or equal to 100 n square? Is this true? C into, obviously, like this is always C into, we need to find out the value of C into n. Is this true? Just think about it. At the first glance it seems like it is not true, but who is stopping you to take C equal to 1 upon 100, right? No one, right? Because C just needs to be some positive constant. If you are taking C equal to 1 upon 100 and n maybe like you can take just 1, after this only this is true, which means you can say 10 n square is greater than or equal to, if you are taking C equal to 1 upon 100, it is actually n square. Yes, this is true, right? This is true, which means this is true, which means you can say that 10 n square is actually big omega of 100 n square, right? Because you have C and n. So anyway, like you will never ever need to find C and n. You can always ignore this 10 and all these constants, and you can put this in the big omega also. Okay, you can always put this in the big omega. And if you are putting this in the big omega, which means if you are saying that n square is actually a big omega of n cube, which means you are saying that n square is less than or equal to n cube, right? C into n cube or n cube, right? So if you are saying like this, then you can always say something bigger than this n cube, which means you can say that sorry, this is greater than or equal to, this is not n cube, this is n, and this is greater than or equal to. So if you are saying n square is big omega of n, then you can always say something which is actually lesser than n, which means you can say that n square is always big omega lesser than n, you can put some value, maybe log n. Log n is actually lesser than n, so you can say n square is also greater than equal to log n, which is also trivial, right? If n square is greater than equal to c into n, then n square is also greater than equal to c into log n, right? So which means if you are able to put some value here, you can always put some lesser value, right? So okay, after examples it will be more clear, but for now I hope you are getting. Let me quickly tell you the difference between big O and big omega. So symbols are clear, right? So here I say Tn equal to big O of Gn, right? Here I say Tn equal to big omega of Gn. Here this means that after a turning point, Tn is actually lesser than equal to C into Gn. Here this means after a turning point, Tn is actually greater than equal to C into Gn. Okay. So if I can say that Cn is less than equal to like Tn is less than equal to C into Gn, then you can also say less than equal to some anything which is greater than Gn, right? Maybe if Gn is n square, then you can say n cube, n power 4, this will also work, right? N power 4. Now similarly, if something, let's suppose this is n square again, if Tn is greater than equal to n square, then Tn will also be greater than equal to something lesser than this, right? It will be greater than equal to n, it will be greater than equal to 1, it will be greater than equal to log n, like that, right? Something lesser than will also work. Okay, so after examples it will be more clear. Let me take more examples. So let's take this example and let's try to find out the value of C and N naught for, let's suppose, big O of, so here it is big O of N. So what will be the value of C and N naught? For that, this is 2. Let's just try to find out it. Okay, so it is 3n plus 2, which is lesser than, sorry, again this is greater than equal to C into N, right? So what do you think? I think C equal to 1 will work, right? C equal to 1. For C equal to 1, I think this is true. And after maybe n equal to 1 only. C equal to 1, n equal to 1, this is true. Again, you will never actually need to find out these values, because you will ignore the constants and you will just simplify this expression to be n. And then you can put this n or lesser than n here. But anyway, just for the sake of practice, let's find out the values of C and n. So it is, if you find out the values of C and n for this, then let's just try it. 10n square plus 4n plus 2 is less greater than equal to C into n square, right? So maybe I think again you can take C equal to 1, and yeah, and after n equal to 1 only, I think it should be true. And what about this? Again I think C equal to 1, this will work in this case also. What about this? Again I think C equal to 1 will work. C equal to 1 will work in these cases, right? So I think that is fine. So I hope you got it. Okay. Now tell me, okay, for now, like you understood this big O and big omega. Now we will move to the different notation. Before that, tell me how much time you will take to prepare a Maggie. Maybe you can say you will take at most 3 minutes, which is too much optimistic. So you cannot, if you cannot guarantee it, it is just for a fun. Okay, not any serious question, just for a fun. Maybe you can say that at least 2 minutes. Yeah, maybe this is true, because at least 2 minutes you will take, right? At most 1 day, yes, this is also true, because at most at most 1 day you will take more than 1 day. Who is going to take just to prepare a Maggie? At least 10 seconds, yes, I think maybe this is also true, right? So you are seeing one thing here, that whenever you are giving the lower bound, which means at least, then you are being too much lower. You are saying at least 10 seconds, which is trivial, right? And whenever you are giving the upper bound, so you are saying that at most like too much to 1 day, which is also trivial. So basically what is happening here, if you go again to this slide, which is big O and big omega, whenever you say big O, you actually bound it to the upper thing, right? You will say that it is never going to take more than this much. It is never going to take more than n square. And if you are saying big omega, then what does this mean? You are actually saying, if you are saying Tn is actually greater than equal to C into n square, right? So what does this mean? It means to say that for any input, okay, whatever is your input, for any input, you are going to say for any input, you will take at least n square time, right? And what does this mean to say? If you are saying Tn is lesser than equal to C into n cube, so it means for any input, you will take at most, right? Because it is upper bounded, right? At most n square time, n cube time. So which means seems like both of these notations are useful, like n square and n cube, both of these notations are useful, which means this big O of n square and big O, oh sorry, big omega of n cube. Okay, again, this is big omega of n square, this is big O of n cube, right? So you will say that yes, big omega means you are telling that at any input, like whatever input is you are going to give at any input, so it is actually called as best case. Like in the best case also, you are going to take at least n square time, which means you give me any input, I am going to take at least n square. You give me any input, I will not take more than n cube. So can you say for any algorithm, can you say this? Isn't it true for any algorithm? Yes, for any algorithm in the world, right? Right? Why? Because it means to say that Tn is greater than or equal to 1, C into 1 or something like that. So obviously, like C, right? So for any algorithm, you will take at least constant time. That is true, right? There is a C that exists, C equal to 1. For any algorithm, you will say that yes, it is going to take at least one time. So this is actually true. This is actually true for any algorithm, right? Isn't it? And isn't it also true for any algorithm order of maybe very large function, like not infinity, but okay, something very large function, maybe you can say some n power n, maybe some large function, maybe, okay, it is extremely large function. Okay, so this is too much of exponential, so it is very large function. So you can say almost for any algorithm this is also true, right? Because your algorithm will never take more than this. I mean, if like you can say that in case of big omega, you can say it will always take more than this, and in this case you will say it will never take more than this, because it is too much of time, right? It is almost infinity. So let me just write infinity. Okay, so you can say that this is of too much of time, because for large value of n and some c, that will evaluate to too much of time, right? So anyway, let me just write infinity if you're getting confused with this. So let me just write infinity here. So for, isn't it true for any algorithm? You can say that Tn equal to order of infinity, right? Which means it will always take less than equal to infinity, and it will always take greater than equal to 1. So for every algorithm this is also true, and for every algorithm this is also true, right? Now, if I ask you that what is the time to prepare Maggie, so you will say this is as good as infinity. You will say that okay, at least infinity time, maybe less than, like greater than equal to 1 minute or greater than equal to 2 minutes. So these are the obvious answers, right? So what I'm trying to convey is that like you might be knowing Donald Knuth. So he is one of the Turing Award winner and a very much famous scientist. So like what happened, like he has given some assignment to his students to find out the time bound for some of the algorithms. Okay, maybe he has given 5 questions. Then most of the people said like, okay, this is bounded by like this, and this is bounded by like this, because they are giving some obvious answers. Like if they were confused like whether it is n square, n cube or something, so they are saying okay, n power 5, who cares, right? I mean, if it is n square, then it is also n power 5, right? So they used to write some bigger values here, they used to write some smaller values here, and he was very tensed because mathematically they are right. I mean, he cannot give 0 marks to all of these questions. Mathematically they were right, but actually they are like it is nonsense. I mean, like it is by default it is true, and for many algorithms maybe like I mean, they used to write some bigger functions here. So this is also true for many algorithms, right? So that is why he invented, there is a different notation which is called theta notation, which is actually saying that you are not going to say Tn is less than equal to something, Tn is greater than equal to something. Tell me Tn is equal to what, equal to, exactly equal to what. Okay, so this theta notation will tell you Tn is exactly equal to which function. So he has invented, there is another notation which is called theta notation, and which is what we are going to see in the next video. So theta notation is got invented by him, and because of this practical case actually. So let's see the theta notation in the next video.